welcome to a new video in our unit on complex analysis. In this video, we'll discover some incredible properties of complex integrals. This video is adapted from Visual Complex Analysis by Tristan Needham. First, we'll derive complex integrals using the idea of Riemann sums. From there, we'll discover that the integral along a closed loop of an analytic function is 0. Interesting things start happening when our loops enclose poles. This will lead us to Cauchy's formula, which we'll use to solve several different problems involving real integrals and infinite sums. For real integrals, the operator, the integral from a to b, is well defined. One way to think of the integral is a sum of the area of discrete polygons under a curve. Typically, the domain of integration gets split up into evenly sized pieces of size delta x. For example, the integral from a to b of f of x dx can be approximated using the trapezoid rule, also called the midpoint Riemann summation rule. The sum from I equals 0 to n minus 1 of 1/2 times f of xi plus f of xi plus 1 times delta x. The trapezoid rule has error of order delta x squared. Other approximations of the integral have different errors, but all must converge to the exact result in the limit that delta x goes to 0. So how can we generalize this idea to a complex integral, the integral from a to b of f of z dz? The start and end points are two-dimensional, but we're only integrating over one dimension. So first we'll have to pick a path gamma that connects points a and b. This is a plot in the z-plane. Let's see what happens after we transfer over the idea of Riemann summation directly. So Rm equals the sum on n of f of zn times delta n. We'll split up gamma into small segments of size delta n. Note that while the magnitude of delta n stays constant, the angle between neighboring segments can and often does change. This is represented by the turning angle, or the difference in angle between segment n and n plus 1. Then we can derive a complex integral in terms of the limiting value of the Riemann sum Rm as delta n goes to 0. Now that we've split up the curve in the domain, what's happening in the w-plane? At each zn, we evaluate the point wn equals f of zn in the w-plane. Unlike the path in the z-plane, the image of f of zn doesn't form equally spaced segments. For our Riemann summation Rm, we're summing the products f of zn times delta n, which equals wn times delta n, which we're going to call delta tilde n. At each value in the summation, wn acts like a conformal factor for delta n, scaling it by the magnitude of wn and rotating it by the argument of wn, which we're going to call tau n, so that phi tilde of n equals phi n plus tau n. Each of these values is a complex number, so we can add them like vectors. Here, I'm showing the sum of the delta tilde n's in another copy of the complex plane that I'm going to call the q-plane. The n plus 1th segment is rotated by phi tilde with respect to the nth segment. Changing the path just changes the values of the tau n's, but their sum remains the same. So as long as our path only passes through analytic points, the value of Rm depends only on the start and the end points. We can use this mapping between the z, w, and q planes to construct an upper bound for the value of a contour integral. If we don't have any bends in the sum in the q plane, then the maximum length we'd have is the sum of the lengths of the delta tilde n's. So the magnitude of Rm is less than or equal to the sum of the magnitude of the wn's times the magnitude of the delta n's. The magnitude of the wn's are the distance between the origin and the points along the curve in the w-plane. Instead of dealing with them individually, we can call L the maximum distance from the origin to the curve in the w-plane. So the magnitude of Rm is less than or equal to L times the sum of the magnitude of the delta n's. The sum of the magnitude of the delta n's are just the total length of the curve in the z-plane, gamma. So the final inequality that we'll use towards the end of this video is that the magnitude of Rm is less than or equal to L times gamma. Let's take a look at some properties of the complex integral. First, the integral along gamma of c times f of z dz is equal to c times the integral along gamma of f of z dz, where c is a constant. Second, the integral along gamma of f of z plus g of z dz is equal to the integral along gamma of f of z dz plus the integral along gamma of g of z dz. Third, the integral along the curves gamma plus eta of f of z dz is equal to the integral along gamma of f of z dz plus the integral along eta of f of z dz. Fourth, the integral along minus gamma of f of z dz is equal to minus the integral along gamma of f of z dz. Let's use the last two properties to derive Cauchy's theorem. We'd like to evaluate the integral along gamma 1 of f of z dz minus the integral along gamma 2 of f of z dz. We can switch the direction of gamma 2 to get the integral along gamma 1 of f of z dz plus the integral along minus gamma 2 of f of z dz. Then we can combine gamma 1 and gamma 2 into a single integral, the integral along gamma 1 minus gamma 2 of f of z dz equals 0. This can be summarized by the integral around a closed loop gamma of f of z dz equals 0, where f of z is analytic everywhere within the domain bounded by gamma. In complex analysis, we call integrals like this around closed loops contour integrals. Let's take a look at the complex inversion mapping. Z goes to 1 over z, which equals 1 over r times e to the minus I theta. We'll use a simple path, which is a circle of radius a centered at the origin. Our discretization has broken this into steps of constant angle phi, starting at alpha equals pi over 2. Each step is rotated from the previous one by the angle phi. The length of each step is the absolute value of delta equals a times phi. Thus, delta equals a times I phi. The image of this path in the w plane is a circle of radius 1 over a, so each step gets shrunk by 1 over a. The angle between steps in the w plane is tau equals minus phi. Thus, delta tilde n equals wn times delta n, which equals 1 over a times e to the minus I phi n times a times I phi times e to the I phi n, which equals I phi. Recall that the Riemann sum, Rm, equals the sum on n of fn of z times delta n, which equals the sum on n of I times phi. If we add these values up like vectors in the q-plane, we get a straight line. The integral along this path, then, is equal to I times psi, which is the total angle of the circular arc. If we were to continue integrating around this circle until our path forms a closed loop, the integral doesn't vanish. We end up with Rm equals 2 pi times I. The only difference between this and the closed loop integral we previously worked out is that this loop encloses the origin, which is a non-analytic point in the complex inversion mapping. As before, we can deform the path as much as we'd like as long as it doesn't pass through a non-analytic point, and the integral remains the same. As you'll see, most of the ideas in the rest of this video will be based on this example. Using the same technique, let's show that the complex integral of a power function f of z equals z to the m is formally the same as its real analog. The integral from a to b of x to the m dx equals 1 over m plus 1 times b to the m plus 1 minus a to the m plus 1. We'll use the same path as in the previous example. It has steps of length delta equals a times phi, which are rotated in succession by the angle phi. Using the conformal factor for the mapping r to the m e to the im phi, we can derive the following. 1. The turning angle for the steps tau equals m times phi. And 2. The scaling for the length of the steps, the magnitude of delta tilde equals a to the m times a phi, which equals a to the m plus 1 times phi. Thus, Rm has steps of length a to the m plus 1 times phi, and turning angle of phi tilde equals tau plus phi, which equals m plus 1 times phi. This gives us a circle. The arc length subtended by each step is equal to the magnitude of each step. Rho times phi tilde equals the magnitude of delta tilde. We can use this to solve for the radius rho equals a to the m plus 1 divided by m plus 1. Thus, for m not equal to 1, Rm equals a to the m plus 1 over m plus 1 times e to the I m plus 1 times psi minus 1. Or equivalently, Rm equals 1 over m plus 1 times b to the m plus 1 minus a to the m plus 1, which is the result we got for the real integral. When we have a closed loop in the z-plane, loops in the q-plane can also close when m plus 1 is an integer. The only case where the turning angle phi tilde equals tau plus phi equals 0 is when m equals minus 1, which means the loop cannot close. Thus, all integrals along closed loops enclosing the origin of z to the m are 0, except for m equals minus 1, where the integral is equal to 2 pi I. Now that we've worked out how complex integrals of power functions behave in the vicinity of the origin, we can generalize what we've learned to more general complex functions. Consider the function f of z, which has a pole at z equals a. Functions like f of z, which are holomorphic except at a set of isolated points ak, which are poles of f of z, are called meromorphic functions. Near the pole at z equals a, we can express f of z as phi of z divided by z minus a to the m, where phi of z is an analytic function and m is a positive integer that is the order of the pole. Near z equals a, phi of z can be expanded in a power series. Phi of z equals the sum from n equals 0 to infinity of cn times z to the n, where cn equals the nth derivative of phi evaluated at a divided by n factorial. Thus, near its pole, f of z can be expanded in the Laurent series. F of z equals c naught divided by z minus a to the m plus c1 divided by z minus a to the m minus 1, etc. through c m minus 1 divided by z minus a plus cm plus 1 times z minus a, etc. Consider the contour integral of f of z around the closed loop gamma surrounding a pole at z equals a. Each term in the Laurent series yields 0 except for the term cm minus 1 divided by z minus a, which gives 2 pi I times cm minus 1. For the pole at z equals a, the coefficient of the term 1 over z minus a in the Laurent series for f of z is called its residue. We'll use the notation res of f and a to denote the residue of f of z at the pole at z equals a. Thus, the integral along gamma of f of z dz equals 2 pi I times the sum on k of the residue of f at ak. This is known as Cauchy's formula. We can use the Laurent series for f of z to come up with a formula to calculate the residue at a pole. The residue of f at a equals cm minus 1, which equals the m minus 1th derivative of phi evaluated at a divided by m minus 1 factorial. This isn't always the easiest to calculate, although many software packages can calculate this for you. We'll work out one formula for one of the most common cases. Let f of z have a simple pole at a so that f is equal to p divided by q, where q has a simple 0 at z equals a. Then the residue of f at a equals the limit as z goes to a of p of a divided by q of z minus q of a divided by z minus a, which equals p of a divided by the derivative of q at a. Since most residues can be calculated by computer, the most important part of contour integration is learning how to pick contours and sometimes how to pick the appropriate integrand. We'll go through a few examples of real functions that can be solved using contour integration and show how to pick the contour and the integrand for each case. Number 1, the integral from minus infinity to infinity of 1 over x squared plus 1 quantity squared dx. Number 2, the sum from n equals 1 to infinity of 1 over n squared equals pi squared on 6, and its surprising relationship with the contour integral of the cotangent of z divided by z squared dz. And 3, the integral from 0 to infinity of x to the 1/3 divided by x squared plus 1 dx. First, we'll look at the integral from minus infinity to infinity of 1 over x squared plus 1 squared dx. Instead of looking at the real function, we'll look at the complex function 1 over z squared plus 1 squared, which has poles at plus and minus I. We're interested in the integral along the real axis of this function. We can often split up contours into a couple of parts. For integrals like this, we can create a contour where one part goes along the entire real line and the other part is a semicircle of radius a goes to infinity. We can rearrange this to show that the integral from minus a to a of f of z dz is equal to the contour integral of f of z dz minus the integral along the arc of f of z dz. We can calculate the contour integral of f of z dz as 2 pi I times the residue of f at I. We can rewrite f of z equals 1 over z plus I squared times z minus I squared. At the point z equals I, the residue is d by dz of 1 over z plus I squared evaluated at z equals I, which equals minus I divided by 4. So the contour integral is equal to pi over 2. Next, we need to show that in the limit that a goes to infinity, the integral along the semicircle goes to 0. We can use the inequality we derived at the beginning of the video to calculate this. The total length of the contour is pi times a, and the maximum value of f of z along this contour is 1 over a squared minus 1 squared. So the upper bound for the integral along the arc is the limit that a goes to infinity of pi a divided by a squared minus 1 squared equals 0. This means that the integral from minus infinity to infinity of 1 over x squared plus 1 squared dx equals pi over 2. The famous result by Euler that the sum from n equals 0 to infinity of 1 over n squared equals pi squared on 6 is related to contour integrals in a beautiful way. Because Cauchy's formula lets us compute integrals based on the sum of the residues enclosed by a contour, we can turn this around to use contour integrals to calculate infinite sums. For infinite sums, like the one here, trig functions are useful because they can be engineered to have equally spaced poles along the real axis. For example, the function the cotangent pi z has simple poles where sine pi z equals 0 at z equals integer values. If we expand the cotangent of pi z in a Laurent series about z equals n, we find that the cotangent of pi z equals 1 over pi z minus n minus pi on 3 z minus n plus higher order terms. This means that the residue of cotangent pi z at n equals 1 over pi. We're looking for something that looks like 1 over n squared. So other than at z equals 0, 1 over z squared is analytic, so it acts like a coefficient for the residue. For n not equal to 0, the residue of cotangent pi z divided by z squared at n equals 1 over pi times n squared. At z equals 0, we multiply the Laurent series for cotangent z by 1 over z squared and look for the coefficient of the 1 over zth term, minus pi on 3 times z divided by z squared, which is minus pi on 3. We can combine this together to show that if f of z equals cotangent z divided by z squared, then 1 over 2 pi I times the contour integral of f of z dz equals the sum from n equals minus n to n of the residue of f of z at n, which equals the residue of f of z at 0 plus 2 times the sum from n equals 1 to n of the residue of f of z at n, which equals minus pi on 3 plus 2 on pi times the sum from n equals 1 to n of 1 over n squared. So how do we calculate the contour integral? From Euler's famous formula, we know that it must vanish. Let's start by looking at the upper bound of the integral on all 4 contours. Under the map 1 over z squared, the largest value it can have is 1 over n squared. Likewise, along the horizontal lines, the magnitude of cotangent of z goes like cosh of y divided by sinh of y, which goes to 1 in the limit that y goes to infinity. For vertical lines, z equals plus or minus n plus a half plus I times y, the magnitude of cotangent of z goes like 1 minus e to the 2 pi y divided by 1 plus e to the 2 pi y, which is always less than or equal to 1. This means that as n goes to infinity, cotangent of z divided by z squared goes to a constant divided by n squared. Each of the contours have length 2n, so that the magnitude of the contour integral of cotangent z divided by z squared is less than the limit that n goes to infinity of a constant divided by n, which equals 0. So the sum from n equals 0 to infinity of 1 over n squared equals pi squared on 6. A further extension of this example shows that the sum from n equals minus infinity to infinity of 1 over n minus w squared equals minus pi times the residue of cotangent pi z divided by z minus w squared, evaluated at w, its only pole. This equals d by dz of cotangent pi z evaluated at z equals w, which equals minus pi divided by sine squared of z minus w. Lastly, we'll take a look at integrals where the integrand has a branch cut in it. We'll solve the integral from 0 to infinity of x to the 1/3 divided by x squared plus 1 dx using the contour integral of z to the 1/3 divided by z squared plus 1 dz. Our integrand has poles at plus and minus I and a branch point at 0, which we need to avoid. Here we want to construct a contour for this integral that does not cross the branch cut, which we'll choose to be along the positive real axis. We'll split our contour into 4 parts. Integrals of this form are sometimes called keyhole contours. First is a circular arc around the origin of radius r oriented clockwise. The second is a line parallel to the real axis oriented to the right. The third is a circular arc of radius R oriented anticlockwise. And our contour is closed by another line parallel to the positive real axis oriented to the left. The two integrals along the real axis are on opposite sides of the contour, so they don't cancel each other out. In the limit that r goes to 0 and R goes to infinity, the integral along gamma equals 1 of f of z dz equals the integral from 0 to infinity of f of x dx. We'll call this I for now, since it's the value we're trying to solve for. The integral on the other side of the contour is a rotation by 2 pi of the original integral. So under the map z goes to z to the 1/3, this acts like a rotation by 2 pi on 3. So in the limit that r goes to 0 and R goes to infinity, the integral along gamma 2 equals e to the 2 pi I on 3 times the integral from infinity to 0 of f of x dx, which equals minus e to the 2 pi I on 3 times I. Now we need to show that the integral along gamma R goes to 0 as R goes to infinity, and the integral along gamma r goes to 0 as r goes to 0. The maximum value for f of z along a circular arc of radius a is the absolute value of a to the 1/3 divided by 1 plus a squared. The length of the arc is 2 pi times a. So the contour integral along that curve is less than 2 pi times the absolute value of a to the 4/3 divided by the absolute value of 1 plus a squared. This goes to 0 in both the limit that r goes to 0 and that R goes to infinity. Cauchy's formula says that the contour integral is equal to 2 pi I times the residue of f at I plus the residue of f at minus I. The residue at z equals plus or minus I is given by z to the 1/3 divided by z plus or minus I evaluated at z equals plus or minus I. This equals minus I divided by 2 for plus I, and e to the minus I pi on 3 divided by 2 for minus I. After some algebra, the contour integral z to the 1/3 divided by z squared plus 1 dz equals 2 pi I times minus 1 plus e to the minus I pi on 3 divided by 2, which is also equal to 1 minus e to the 2 pi I on 3 times I, which is the integral we're trying to solve for. Thus, the integral from 0 to infinity of x to the 1/3 divided by x squared plus 1 dx equals pi divided by root 3. I hope this video has helped you understand the contour integral and some potential uses for it. Thanks for watching, and I'll see you next time.